Kia ora Year 12 and Year 11. I've had some requests to go over this year's algebra exam, so I thought I would give it a go. This question that I'm going to do first is the one about the cubic with the orange and the blue line. I'm going to go pretty slowly, and there are three parts to the question. So first I'm going to look through the questions and make sure that you're reading the question really carefully, because the diagrams and the words give you a lot of clues about what you need to do. So this question is about mathematicians in the 16th century when they were trying to figure out how to solve cubic equations. And one of the things they worked with was a thing called a depressed cubic. And this is an expression in the following form. So you don't need to know any of that, but they've given you the equation. The equation is this: y equals x cubed minus 12px plus r. So just notice there's no x squared in there, which is why it's called a depressed cubic. It's missing that term. There are heaps of fantastic maths books out there that tell the story about what happened back in the 16th century with this, but I guess right now you just want to know how to do this question. So here we're given a specific case in which we've got a graph of this function, and we're told that it passes through point A, and point A is at 440. So this is kind of like the warm-up part, and it says find an expression for P in terms of R. So what I have to do here is to take this point, 440, substitute it in here, and rearrange to get P equals blah, blah, blah. So let's do that now. So we have 40 is equal to 4 cubed minus 12p times 4 plus r. So 40 is equal to 64 minus 48p plus r. I'm going to rearrange that and get p to the left-hand side. So 48p is equal to 24 plus r. Dividing everything through by 48 gives me p equals 24 over 48 plus r over 48. P is equal to 1/2 plus r over 48, or you could write that as 1 over 48 times r. Okay, so that's the first part. Let's look at part 2 now. So this time, I'll just make that a bit bigger. We're still working with this specific curve, and we're told that at point B, it's true that 3x squared minus 12p is equal to 0. Okay, so we have to use algebra to show that at point B, x is equal to this. So actually we're now moving away to any member of this family, right? So we're working with this. This is my function. And we're told that at that maximum point, this condition must be true. If you've done level 2 calculus, you'll be able to see that we could get to that separately by differentiating. But here, they've given you that condition, and that's because we're working on an algebra standard here, right? So here what we have to do is to show that at point B, x must be this value. So we have 3x squared minus 12p is equal to 0. Dividing through by 3 gives me x squared minus 4p equals 0. We know that at point B, x is negative, right? So the x value that we're going to get has to be less than 0. Rearranging, we get x squared is equal to 4p, and there are two solutions to that. X can either equal what can be the positive or the negative root of 4p. So x is equal to negative 2 root p or 2 root p. But we know that x is negative, so we have x is equal to negative 2 root p, which is what we were asked to find, and we can rewrite that now as p to the power of 0.5 as required. Okay, let's just check we've answered the question. Okay, so that's all we had to do here. Using algebra, show that x is equal to negative 2p to the power of 0.5 at b. So the part that I think really needed you to be quite calm and read carefully is the third part. So we're told that when we've got one of these cubics, right, x cubed minus 12px plus r, the shape of the curve is going to change when the p and r numbers change. And when that happens, they've given us a coloured picture here. And the lengths of the orange lines and of the central blue line vary. But these two lines here will always be the same length. And you can see that the length of that orange line links back to kind of to what we had in the last question, right? Because it's this length here. I'll try and do this in orange so I don't confuse things more. So this is the length of the orange line, right? And then we're looking at the length of the blue line. And when we change the values of these numbers, the curve wiggliness is going to change. So then when we read on, we're shown 3 examples from when we change P and R, right? So we've got these 3 examples of cubics. And we're told that sometimes the curve can intersect the x-axis 3 times. That's what's happening here. We've got 1, 2, 3 roots. Here, we've just got 2, and here we've just got 1. So what we have to do, well, we're told that this is going to happen, this case, where it intersects 3 times, is going to happen if the orange line is longer than the blue line. And we have to find the condition that P and R must satisfy for the graph to have 3 distinct x-intercepts. We're going to come back to this. This is how we have to write our answer. But let's figure out what this means in terms of these orange and blue lines and how we can find their lengths. Well, we're told that we'll have this case here if the orange line is longer than the blue line, right? It says each orange line, but we know that the orange lines are the same, right? The orange lines are always going to be the same length. So coming back to here, let's see what the length of the blue line is first. Well, the blue line goes from here up to here. This point here is simply the y-intercept. So at this point, I think it's useful to write this, instead of y equals, I'm going to write it as f of x equals. So we know that we can find the y-intercept by substituting in x equals 0. So f of 0 is just equal to r. That means that the blue line has length of r. So let's start writing some of this down. I've got another picture here for us to use. So the blue line has length f of 0, which is just equal to r. Now let's look at the orange line and see how long that is. Well, we can work with either of the 2 orange lines. I'm going to stick with the one we're familiar with over here. So the orange line goes from here down to here. So how high is point B? What's the y coordinate of point B? Well, it's the value of the function at negative 2p to the power of 0.5, right, minus f of 0. So there's lots of ways to see this, but I think if you pause the video and stare at it, you'll see that the orange line is all of that, take away that, right? But it's very easy to find this length. We've already done that. That's just the y-intercept. Okay, so what we're being asked to find is the conditions when the orange line is longer than the blue line. Okay, so pause the video at this point and try and finish this question off from here. Some of you will be going, well, why doesn't she work with the nice positive value here? you can do it that way as well. Okay, but in that case, you're going to have the orange line length will be f of 0 minus f of 2p to the 0.5. Okay, they're going to give you exactly the same thing. So the orange line length is going to need us to work out this, f of negative 2p to the 0.5. So we're going to substitute that in to my cubic. Remember that f of x was x cubed minus 12px plus r. So in here, we're going to substitute in this. Okay, so let's just work that through now quickly. And we're going to get negative 8p to the power of 1.5 plus 24p times p to the 0.5 plus r. Now when you look at this, this is just 24p to the power of 1.5. I'd much rather be saying that as 3 over 2, but because the question worked with 0.5, I'm sticking with that. So this simplifies to give me 16p to the power of 1.5 plus r. But remember, that just gives me the height here. Now I have to subtract off r. So that's going to simplify the expression. So the orange line length is f negative 2p to the 0.5 minus f of 0, which is 16p to the 1.5 plus r, take away r, which is 16. Now I'm going to write that as p to the power of 3 over 2. So the condition we need is when is the orange greater than the blue. So 16p to the 3 over 2 has to be greater than what? What have we got for the other one? 16p 3 over 2 is greater than r. Right, so let's just rearrange it. So we've got p to the 3 over 2 is greater than r over 16. And the question asked me to give my answer in a form where the exponents of p and r are both positive integers. So I can't leave it like this, although you've probably got most of the marks in the question if you've got this far. I'm going to now square both sides. So we have p cubed is greater than r over 16 squared, which gives me p cubed is greater than r squared over 256. Okay, I'm just checking that that's what I got when I did it earlier. Another way to write that is this. Now I've just got time to show you in Geogebra what this looks like. So that's my final answer. So I did some screenshotting in Geogebra. I'm going to hop over to Geogebra now and see if it's going to work. So what I'm doing here is you can see on that screen that I'm moving a slider around, and you can see that now it's got 3 roots, and now it's only got 1 root. A couple of examples are on the next pages. So this is one that I did before I made the video, where I've looked at the value of p cubed minus r squared over 256. So I've looked at this value and it's a positive number, and you can see that it's cutting through 3 times. Down here I've got one where it's a negative number, and you can see that it's only cutting through once. So you can do this yourself using Geogebra if you just set up the cubic and then put in 2 sliders and change the values. And if you don't know how to do that and you want a hand, just leave me a comment and I can email you back and explain. So there you go. That was a pretty involved question if you weren't confident, but they did give you a lot of places where you could see what the next step was. So the key, I think, to the hardest part in here is the idea of the orange and blue lines. So just one last time, this line here is coming from the y-intercept. This line length here is the difference between this y-coordinate and this y-coordinate. Thanks for watching and have a good Christmas holiday.